All right, so get ready for a deep dive today. We're going to be looking at computer architecture, specifically something called the CRISP instruction set. And from what I can tell, this isn't just another computer chip. It's more like a finely tuned instrument for efficiency and speed. You've sent over a bunch of papers on this, and I have to say I'm pretty interested to get into it.
Well, what makes CRISP stand out is that it's classed as what's called a reduced instruction set computer architecture, or RSC for short.
Okay, RSC, yeah. That's taking me back to computer science class. Isn't that it usually means a focus on speed, right?
Yeah, that's exactly it. RSC architectures are, well, they're designed to be as efficient and fast as possible. So they get rid of all the extra baggage that some architectures have and just streamline everything. They concentrate on a smaller set of instructions, and these instructions can be executed really, really quickly. But, and this is where it gets interesting with CRISP.
Oh, I knew there had to be a twist. It couldn't be that straightforward.
CRISP, well, it does things a bit differently compared to other ISC machines. It's got a unique design that gives it a real edge, especially when you're running programs written in C. It's like, imagine you got a race car driver, right?
Yeah.
But this driver only speaks Italian. Put them in a Ferrari that's designed to respond to Italian commands, and, well, you can bet they're going to perform at a whole other level.
So CRISP is like the Ferrari of the C programming language.
Right.
That's a great analogy.
Yeah.
It's like it's built from the ground up to make C code, well, sing. And this is where all those technical papers you gave me come in, right? Oh, what about this stack thing I keep seeing?
You're right on the money. CRISP uses a stack, which is a special kind of memory structure, and it's used to manage how data moves within a program. Think of it like a waiter carrying a stack of plates. They can really only access the top plate easily, right? Well, it's kind of like that with CRISP and its stack. It's a focused approach to data, and it just works really well with how C code is structured. Very efficient.
Okay, that analogy actually helps a lot. So instead of digging through a whole like cabinet of plates, CRISP just neatly stacks them for quick access.
Got it.
Yeah.
So what's next in our crash course on CRISP?
Let's talk about memory. I mean, it's a pretty important part of any computer, and CRISP uses this really elegant concept called the accumulator.
Memory. This is where things usually get a little fuzzy for me.
Hmm.
Is CRISP's memory model, is it as streamlined as its other features?
Absolutely. So picture the accumulator like a workbench, right? But it's inside the computer's memory. It's where most of the data operations happen. And instead of constantly moving data around to different spots in memory, it brings the data to this central workbench, this accumulator, makes processing a whole lot faster.
Okay, so it's like having all your tools right there in front of you instead of having to like rummage through drawers every time you need something. Makes sense. That's smart. Exactly. It's about getting rid of any unnecessary steps. That's a big part of CRISP's design. Maximum efficiency. Now, while we're on the topic of data, we should probably touch on how CRISP handles data types.
All right, data types. I know computers can be picky about those. What's CRISP's approach?
You're right. Data types are, well, they're essential. Now, at its core, CRISP is a 32-bit machine. What that means is it processes data in chunks of 32 bits. It's like its native tongue, you could say. But CRISP is actually multilingual.
Multilingual. So it can handle more than just these 32-bit pieces.
Exactly. It can work with smaller chunks too, like bytes. It converts them without breaking a sweat, really. Like, imagine a translator switching between languages effortlessly. That's CRISP with data.
So no matter what size, CRISP makes sure that all data is processed efficiently. That's pretty immersive. So how about decision-making in a program? How does CRISP handle that?
Well, CRISP simplifies comparisons. It uses a single true-false bit, which is kind of like a light switch. It's either on or off.
So instead of like a whole spectrum of maybes, it's a definitive yes or no. That must make the code really efficient.
Absolutely. That straightforwardness, it's a recurring theme in CRISP. Prioritizing efficiency, but without sacrificing what it can do. It's a balancing act that CRISP, I have to say, handles quite well.
It's like CRISP is, with every single line of code, it's making a judgment call. All right, true, we're good to go. False, we're switching gears.
It's amazing how something so simple can be so powerful. But what happens when CRISP has to, like, interact with the operating system? You know, like accessing files or talking to other programs. What happens then?
Well, that's where these things called system calls come in. It's kind of like, imagine you need to ask a librarian for a specific book, right? You wouldn't just barge into the stacks and start searching on your own, would you? You'd use their system, their rules, to request it. System calls are kind of CRISP's way of talking to the operating system.
So instead of making a mess in the library, CRISP plays by the rules and asks for what it needs. I like it. Yeah, exactly. And what's really interesting is that the way CRISP handles these system calls, it's very similar to how the Unix operating system does it. And that makes it really, really easy to integrate CRISP into systems that already exist, especially ones that have, that Unix background.
That makes sense, especially given, CRISP's history. Coming from the Bell Labs C machine project, which was, very tied to Unix. So CRISP is not just efficient, it also plays well with others. But let's be real, no system is perfect. So what happens when something unexpected comes up in the con, like a glitch in the matrix, you could say?
Ah, those glitches, we call those exceptions. And yeah, they're bound to happen. It's part of programming. It's like, when you've got a recipe and it says, don't burn the dish. Easy to say, much harder to actually consistently do.
So how does CRISP handle these inevitable cooking mishaps, but in the code?
Well, CRISP it's actually really good at handling these exceptions. So instead of letting the whole program just crash and burn, it it catches the error, right? And then it makes a note of what went wrong, and it gives you this helpful information that you can use to debug. It's like a smoke detector, alerts you to the problem without setting the whole house on fire.
Okay, so more of a controlled evacuation than a five-alarm fire.
Gotcha.
That's got to be so valuable for programmers. Those debugging clues, they're like gold. This whole architecture, it's really quite impressive. Is there anything that CRISP doesn't excel at?
Well, it's not so much about what it doesn't excel at. It's more that there's another area where it really shines, and that's code density. Remember how we talked about RISC being all about efficiency? Well,
Yeah.
CRISP takes it a step further by packing its code incredibly tightly.
Code density, is that like writing a whole novel on the back of a postage stamp? How do they even do that?
You're getting the idea. CRISP uses something called variable instruction length. So some instructions, the ones that get used all the time, those are like the workhorses. They're made smaller, more compact. They use less memory. And then others, the ones that are maybe more specialized, they might take up a bit more space.
So it's like having a toolbox where the tools you use all the time, they're right there on top, and
Right.
then the more specialized stuff, it's tucked away, but it's still easy to get to.
Exactly. That's a great way to put it. And the sufficient use of memory, combined with that compact instruction set we talked about, it all leads to much faster execution times and just overall a smoother operation. It really shows how focused CRISP is on squeezing out efficiency at every level.
It's like CRISP is playing Tetris with its own code, just to find those perfect fits, to get the most efficiency. We've gone over a lot from IC architecture to stacks and accumulators and even system calls and code density. I'm starting to see why you find this CRISP architecture so interesting, so fascinating.
It's an elegant way to solve a really complex problem.
Right.
And what makes CRISP stand out is, for me, is that it really embodies a certain way of thinking about computer architecture. It emphasizes the clean design, making sure things run efficiently and making the hardware and software work together, in harmony.
It's like CRISP it's more than just like a list of instructions. It's almost like a philosophy, a different way to think about computing in general. Makes you wonder what's next for computer architecture. Are there other, kind of radical designs out there just waiting to be discovered?
Oh, I'm sure of it. This field, it never sits still. New challenges pop up, and we need even more innovative solutions, right? Like right now, we're seeing some really cool stuff happening in things like parallel processing, where you can run multiple tasks at the same time, and even neuromorphic computing, which takes inspiration from, believe it or not, the human brain.
Wow. Sounds like we're on the edge of a whole new era of computing. One where, well, the only limit is our own imagination, really. And if CRISP's any indication, the future of computer architecture is going to be really, really exciting.
I think so too. And what's particularly interesting to me is how all of these new advancements, how they're going to change the way we use technology, how we interact with it. Imagine a world where computers aren't just tools. They're like extensions of our own minds, of our cognitive abilities.
Wow, that's both exciting and a little bit intimidating at the same time. This whole deep dive, I've got to say, it's given me a lot to think about. I always knew there was more to computer architecture than, what's on the surface. But seeing CRISP and how elegant it is, how efficient it is, it's really opened my eyes. So thanks for taking me through this. I really appreciate it.
Happy to do it. That's what it's all about, right?
Yeah.
Sharing the joy of discovery.